Okay, so we're doing the nuclear chemistry, and there we go. So first we're going to calculate the mass of silver deposited at the cathode during the electrolysis of silver nitrate solution if the current is 0.10 amps for 10 minutes. So this is actually, I think, a little bit mainly from our last section, but we're going to go ahead and do that today. First off, questions. So what we do know is that we have the 10 amps for 10 minutes. That's what they give us. So we're going to go ahead and multiply that out then. So we have 10 amps. Yeah, that's not let you type it for 10 minutes. And we need to put this into seconds. So we're going to go ahead and multiply that by the number of seconds in a minute. So we have 60 seconds per minute. So then we have it in seconds, because that is going to cancel out this. Whoops. Didn't do anything good because I hit the wrong thing. Cool. All right. Then this is where we're going to use the Faraday's constant number. So we know we're going to have 1 mole of E minus, 1 mole of electrons. One of those for every 96,500 amps times seconds. Honestly, we can just leave that as a S instead of seconds. That's typically the shorthand for it. So then we have that. So now we've canceled out amps per second we have on the bottom here. So we can cancel that out to cancel out our seconds here. And our amps here. All right. So then once you've done that, you can go ahead and switch it over to what it needs to be, because we have it into moles of electrons. So we can look at this, and we're going to have 1 mole, because this is the equation for this problem, the mass of silver deposited at the cathode during the silver nitrate. So if we when we write out the equation, we can see that that's going to have 1 mole of silver for every mole of electrons that are being transferred. So we have that 1 mole of Ag plus. Whoops. For every 1 mole of E minus. And that's going to cancel out then. And that's going to cancel out this. Okay, so now we're in moles, but it asks for it in grams because that's for mass. So we're going to have to go ahead and multiply that by the molar mass, which is going to be 107.87 grams per mole of the silver nitrate. So we can go ahead and get rid of that. Oops. And that cancels out. So then we're going to solve that and see what it ends up as, because we've gotten it to grams, which was our goal. And we end up with 0.0671 grams of silver. Of the silver plus ions. But if we look at our problem, what they gave us had, we're going to say 2 sig figs. Probably should have put a decimal here. They're usually not going to want it in just one, so we're going to go ahead and just change that. Just 2 sig figs. How long would it take to deposit 0.65635 grams of copper at the cathode during the electrolysis of copper 2 sulfate solution if you are using 1200, or not 1200, 0.2 amps? So for that, once more, we're going to go, okay, what did they give us? So they gave us the amount of copper in grams. So we have our 0.635. Got some weird formatting going on here. Cool. Okay. Grams. And that, whoops. And then we know we also, okay, so we can go ahead and put our copper into moles. We'll go ahead and put our unit here since we're starting out and we don't know what that is technically. There. Okay. So then we're going to go ahead and turn it into moles. So to do that, we're going to have 1 mole per 63.55 grams of copper. Okay, so now we've canceled out grams and grams here. So got rid of this. And then I'm just going to leave the copper. Well, we'll cancel it anyway eventually, so let's go and do that. So now we just have a mole of copper, or we have it in moles of copper now. So we need to move it into the moles of electrons. So we're going to go ahead and if we looked at our equation, we would see, and you can kind of see that from having this 2 plus here, that there's 2 moles of electrons being moved across. So we're going to have 2 moles of electrons. For every 1 mole of copper. Okay, so our moles have canceled out our moles of copper. So next we're going to go ahead and we're going to have to multiply by Faraday's constant again. So we're going to look at that. And we know that that is going to be our 96,500 amps times seconds over moles of E minus. All right, so we're going to be able to cancel our moles of E minus. And then after that, all right, so next we're going to have to get it into, we're looking for time. So we've got it into amps. And we know that since we need to get rid of the amps here, we can go ahead and divide it by the number of amps that we actually have. So we're going to go ahead and multiply that by 1 over 0.200 amps. And then our amps are going to cancel out. Oops. Okay, so our amps have canceled out. So next we're going to go ahead and we have it in seconds. And that's and it asks for it in hours. So we're going to say we have 60 or 1 minute is for every 60 seconds. And then we're gonna go okay, but then we have 60 or 1 hour, sorry, keep putting it upside down. For every 60 minutes. And then we're gonna go cancel that out. And then we cancel our seconds as well. Right here. Oh, this whole thing cancels out. Sorry, I forgot to cross out the amps right there. So now we have it in hours. So you'll be able to do your math. And when you solve everything up, you should get, it's going to be 2.6 hours. 2.68 hours. Okay. All right. What is an atomic number? Just getting more into what this chapter is. It's going to be stubborn. I don't think. No. Why is it not working? Okay. I might already have that here. So your atomic number is now, it'll let me type. Sweet. Okay. Atomic number is the number of protons. Protons in an element. So the same element is always going to have the same number of protons, and that'll never change. So all of this like that? That's weird. Yeah, it is. We didn't have answers to there. That's weird. Okay, I'm gonna do this so I'll quit being weird. I've got some weird formatting going on. So now we're going to use atomic mass. So the atomic mass is your total number of what? That's weird. Perfect. Yes, it's the total number of protons and neutrons in the nucleus. So that number can change. It's not always the same. They can have different number of, because they can have different number of neutrons in the nucleus. Perfect. What is an isotope? So an isotope is going to be, it's going to be variations of the same element, but they're going to have some differences in what? Protons, neutrons, electrons, what is they going to have differences in? They will have a different mass number, but what is changing? Perfect. Not protons and neutrons. Perfect. That's exactly right. So it's going to have different numbers of neutrons and a different atomic mass as a result. Sweet. What are the 4 types of radioactive processes? That we're, yeah, here we go. So there, we actually am here. So we're gonna have, there's the 4 different kinds, and they're gonna be beta decay, emissions. We're gonna have alpha decay, which is emissions, and we're gonna have positron emissions, and we're gonna have electron capture. So they're all emissions except for the one kind. So here we have it here. Not both. Wrong answer. Here we go. So I don't think. So I can. Let me see if this will work. So another. Okay, I'm not sure this is going to paste right, but we're going to try it. Nope, it didn't work. Okay. I can type it, it just won't look quite the same. Okay, so there are 4 kinds here. And give you kind of the visuals of what that looks like. So this one are beta decay is going to look like this right here. Oops. So those really should be like right on top of one another, but I can't type it exactly like that. Our alpha decay is going to look like this. The E here is like electrons, like it normally is. Here. We have our helium there. Our positron emission is going to look like our electron emission here, but backwards. I don't know, maybe we should put negative. Not sure. So our positron emission, instead of, it's like adding a positive version of an electron, kind of. So it's going to be still the mass number up there of 0, but it's going to have a positive 1 here. So there it goes. Okay, and that's also here. See if I can spread these out some. That's really close together. There we go. It's a more readable. So our electron capture is also going to look just like this, but it's going to gain 1 instead of losing 1. So using uranium-238-92, complete the following problems. So we're going to have alpha decay. So alpha decay, so what this means is we're going to start out with this. And then and for once, that's not supposed to be a double-sided arrow. That's actually just single-sided. And so we're looking at alpha decay. So we're going to come up here, and we're going to look at this, and we're going to go, okay, so this is what our alpha decay looks like. So we're going to produce one of those. And what else? So we know we're going to produce uranium, but we have to figure out what the numbers are going to be in front. So kind of like when we were doing the problems before and you had to make both sides equal, this is the same thing, except we have to look at these little numbers. And let me make this. So that's something I thought was interesting the other day. So I can do this and make it big here and have more space to look at things. Okay. So like we were talking about, it's going to have the helium and uranium, but uranium what? So we have to figure out how to balance two sides with that. So if we have 238 here, and we're going to have whatever's over here is going to have to add up to 238. So we're going to look at that. And yes, you would just subtract. That's exactly right. So you can take your 238 minus that 4. And then you got your, then you come up with what on top? 234 over 90. Perfect. Y'all are smart. 34 over 90. And that's going to be your uranium. There. Okay, so beta decay. So once more, we're going to have our uranium here. We're going to start with that. So beta decay. And come look and see what that was. Sorry, got something we can't see that. There we go. That's better. Okay, so beta decay is going to be this one. So it's going to lose that. So just like before, you're going to have to take your uranium and figure out the numbers. So what numbers are we going to have on this one? Oh, actually, wait. This is not uranium. I apologize. Let's take a step back real quick. So we have our atomic number on the bottom. So uranium's atomic number is 92. So this one's 90, so that can't be uranium. So if you look at a periodic table, then you can go find what 90 is instead of 92. And we see that that's thorium right here. So we're going to have to go change that to the TH. Apologize, forgot to have changed that last time. Okay. So this time we're looking and the bottom number is going to change again. So it's also not going to be uranium. So what are our two numbers going to be? What's going to go on top? $238, perfect. And what goes on the bottom? Going to do this minus this. What do you think? 92 minus -1. So it's just 92 plus 1. 93. Hey. Yep. Y'all got it. Perfect. So now we're going to look back at our periodic table and look and see what 93 is. So then we have the neptunium there. So that's going to be what our element is that we came up with. So you can see as this radioactive decay is happening, it's actually changing what element we have. Just kind of interesting process there. Okay. Okay, so now we're going to have our positron emission. So once more, we're starting with our uranium 238 over 92. All right, so let's go see what positron emission looks like. So once more, it's an emission, so that's going to be on the right side of the equation. So we're going to have this. And let's see, 238 over 91, you see that through, that's perfect. That's exactly what we're going to have. 238 over 91. All right. And so somebody who hasn't answered yet, since our number down there is 91, what is our element going to be this time? Perfect. It's going to be, oops. So it's going to be proctanium. I was like, I don't know how to say that one. Proctanium, PA. Perfect. Right, now we're on to electron capture. So we're starting out the same way once more. This time, we're doing electron capture. So we're capturing this electron instead of losing it. So it's actually going to be on the left side of the equation, which is kind of strange compared to the other ones. So what are we going to come up with for this? Would you add? Yes, you're going to add them together because you need whatever's over here to equal what's over here. So perfect. 238 over 93. Not quite. You're almost right. You're 238's right. Look at the bottom again. Over 91. Perfect. And so same element as last time. So we see have the 91 here and here. So we're going to have our petronium, I believe it was. So there you've got it. And they use the uranium for these a lot. But I think there's some other things they'll work with too, because like you could have another emission from this TH here, the rhonium, I believe it was. And so you could have like another emission come from this, and you could end up with 2 helium atoms and like 230 over 98. I mean, not 98, 230 over 88. So you'd have to look at your table and go find what 88 is, which is right here. So then you'd have radium if that happened. So, yep. Complete the following problems and label what type of nuclear reaction it is. So we have this, so we have to figure out what we're putting in the middle here. So what are we going to put in there? What is our top number going to be? It's going to look a lot like the problems before. What do y'all think? It's just going to be like before. So we have the 40 over 19 over here. So we're going to have to like subtract this to get to that. So we have 40 minus 0. So on the top here, we're going to have 40. Perfect. 40 over 20. That's exactly right. Oops. 40 over 20. And so what element is that going to be? Perfect. Calcium. So we got our calcium there. And what type of nuclear reaction is this that we're looking at? So we see that it's on what we have here is on the right side. And so that means it's going to be an emission. And so, yep, put beta. That's right. Make sure you put beta decay, though, not just beta, because they can just be like, yeah, so there's beta waves and things like that too. So make sure you write decay, which I know you're just typing shorthand things, so that doesn't matter. Just so you're aware. some professors, I don't know how much of a stickler Bell is for that, but I know that some of my professors have been a little bit of stickler for that. So what do you come up with that we're going to have in this problem? What's going to be our top number? Perfect, 14. All right, what's the bottom number going to be? Not 7. Look at it one more time. You'll see what you messed up on. You have to be careful with that. I've done that plenty of times. 5, perfect. All right. So what is our element going to be this time? Boron, perfect. So it's going to be boron. And what type of nuclear reaction is this? Perfect. It's going to be a positron emission. Okay. So we can go on to the next one. All right. So what are we going to come up with for this reaction? (241 over 94). Perfect. 241 over 94. Okay. And so what element are we going to have this time? Plutonium. Perfect. That makes me think of Back to the Future. Let's see. All right. Oh, and then what kind of a mission is that going to be? Or not necessarily a mission. What type of nuclear reaction is this? Electron capture. Y'all got the hang of this. Y'all are doing awesome. Okay. All right. What are we looking at here? What's our top number going to be? (127). Okay. And what's going to be the bottom number? There it goes. Okay. And our bottom number? Over 51. Perfect. And what element are we going to have? Perfect. of our antimony. And what kind of emission is this? Or I guess this one is actually emission, but what kind of nuclear reaction is this? Alpha decay. Perfect. All right, what is a radioactive decay series? So a radioactive decay series is where it's a sequential process that occurs if the first step does not result in a stable nucleus. The unstable nuclei will continue to react until a stable nucleus is reached. So that's what I was actually talking about above. So kind of like it could happen here. That if you, so say this wasn't stable right here, then you could actually have this go ahead and happen again, and then you end up with 123 over 49, and then what element's 49, and you end up with indium. And then say indium's not stable, so it happens again, and you have another alpha decay, and it can continue just to go down like that until it reaches something that is stable. What kinetic pattern does radioactive decay follow? So, sorry. So it follows first order kinetics. This means that the half-life will be constant. Yep. So, that's all I've got for you guys today. If you need me to go back anywhere on the worksheets, you can see it again, or have any questions, feel free to stick around. I'm going to go ahead and end our recording.